Hi, so in this video, we'll be talking more about backpropagation and how you take gradients when you have a neural network. As a motivating question, which I covered in lecture, we can consider a classification problem where we have a neural network with no hidden layers. What would you call this neural network? So throughout this video, there will be various opportunities where you can pause the video. This is a good time to pause to check your conceptual understanding. All right, so in this case, if we have a neural network with no hidden layers, we actually can just call this logistic regression, which we've previously discussed before in class. Remember, the idea behind logistic regression is we try to learn a linear mapping from our inputs to our outputs, and we apply a sigmoid in the case of binary classification or a softmax function to squish our y's into probabilities between 0 and 1, at which point we apply our loss. So a neural network is really just the composition of these sort of functions. More concretely, we can draw out this diagram where we essentially just copy whatever happens in this linear plus nonlinear layer several times, and that makes a fully connected network. So if we had one hidden layer, our neural network would potentially look something like this. And we can imagine repeating this process more times. So with this sort of framing, you can view logistic regression as a special case of neural networks, or neural networks as a composition of multiple simpler units. So at a high level, what we're trying to do today is, in last lecture, we looked at this function f, which is composed of a bunch of weights and biases, W1, B1, W2, B2, and so on, depending on how many hidden layers you have. And we talked about the expressivity of f. Today, we're going to try to take gradients. So in particular, we want to know how the loss changes with respect to W and B. So we want partial L, partial W, 1, B1, and so on. And the end goal is we're going to try to update the weights and biases of our neural network using the gradient descent algorithm. So just as a high-level recap page here, what we're trying to do is we randomly initialize our neural network. And then if we're running the SGD algorithm, what we do is we sample many batches. So X sub I and T sub I from our data set. And as a motivating example, we can consider the MNIST data set. So we might sample a picture of a 2, and the TI here is going to be the label 2. And that's the goal of what our neural network is trying to learn. We're going to compute the prediction of our neural network. So y is equal to f of xi. And this is also a function of the weights of the neural network. So oftentimes you denote the weights and biases of a neural network as a single long concatenated vector. So we can use theta in this case. Theta refers to the weights and biases. We measure how our predictions are relative to the targets. So we define a loss function, which is a function of our prediction and the targets. So maybe we can rewrite this as compute loss L as a function of y and t. Okay, so once we have our loss, we essentially want to update the weights and the biases, so the theta vectors, to minimize that loss. You can imagine initially when we initialize our neural network randomly, our predictions are going to be very off. So our goal is essentially just to try to nudge the weights so that we're more likely to predict a 2 for this particular example. So the next step, which is the focus of today's lecture, is compute gradient of theta with respect to the loss, which is a function of y and t. So we're trying to figure out how our predictions change. So remember, y is secretly a function of f of x and theta. And finally, once we have this gradient value, we're going to update our parameters. So theta n plus 1 is equal to theta n minus eta, or alpha, which is the learning rate, times the gradient. So we'll define this to be partial L partial theta. And this is the learning rule, which we also considered before in the case of linear regression or logistic regression. So the rough idea here is we're going to nudge the weights so the next time we see the image of a 2, we're a little bit more likely to predict a 2. And then for stochastic gradient descent, you just repeat this procedure again, where you, again, sample a new image and its corresponding target, feed it through our neural network, compute the loss, and then you backpropagate to find the gradient with respect to the current parameters, then you update the parameters. Oftentimes, we rather than just focusing on a single example at a time, we can consider a bunch of different examples. But conceptually, it's probably easier to just focus on one example. And when you deal with multiple examples, you're actually just averaging over the gradients of individual examples. So throughout this video, we'll just focus on a single example at a time. Okay, so the slides describe what I said in words. Our goal is to define this loss over training examples, and today we're going to talk about this really computationally efficient way to actually compute the gradients. So as a motivation, we'll consider a simpler problem first, where we're just looking at this problem where we define a linear function of the parameters. So this is a linear function. We apply a sigmoid. And then I guess in this case, presumably our targets are between 0 and 1, which is why we apply the sigmoid. And our goal is to do a regression task. So we have this loss, which is 1/2 y minus t squared. So you might call this the logistic least squares problem. And the thing to note here is what we'll be using throughout this lecture is this idea of a computational graph, where the nodes of the variables denote the variables that we're trying to compute, and then the edges represent the connections between the different variables. So functions that are applied from going from one variable to the next variable. So in the case above, you can see that z is a function of w, x, and b, and then y is a function of z, and L is a function of y and t. So in general, when we're dealing with functions in this class, we'll have directed acyclic graphs, which means there are no cycles, and that's important when we talk about backpropagation. Okay, so in general, the key tool we'll be using throughout this video is the idea of the chain rule, which says that if you have this set of functions, z equals f of y and y equals g of x, then if we want to compute the derivative of how z changes with respect to x, we have to figure out the effect of x on y and the effect of y on z, and then we multiply the two quantities together. So this should be familiar from a previous calculus class. And because we're just dealing with univariate functions in this first example, we can directly apply the chain rule. So the way you would do this problem in calculus class is you would write out each of the derivatives in turn to get your final expression of how the loss changes with respect to the weights and biases. But this ends up resulting in a really confusing mess of different symbols. And we're going to try a different approach. So you can think mentally about what are some potential disadvantages of this approach. So the two main disadvantages are this is really computationally expensive. Mostly because we're repeating a bunch of different operations. And then it's also really easy to make a mistake. It's complicated, and this seems like something that's challenging to actually implement in code. So the advantage of the backpropagation algorithm is it's going to fix both of these potential pitfalls. It's going to be relatively cheap to run, and also each of the nodes is stored nicely in variable form. So if you were to implement it in code, it's harder to make a mistake. You still do have to be careful, though. All right, so let's just go ahead and work through how you would do this example with the computational graph. So if we were to look at the chain rule, and if we were trying to calculate the expressions partial L, partial B, we note that B affects Z, and then Z affects Y, Y affects L. So we can decompose this into a product of three terms. Partial Z, partial B. And similarly, we have a similar decomposition for W. So we have partial L, partial W equals partial L, partial Y, Y, partial Z, and then partial Z, partial W. So namely, when you write out the chain rule in this form, you'll realize the first two terms are completely the same. So we can go ahead and express these local derivatives more compactly. So if we look at the partial L, partial Y term, this is just going to equal Y minus T. And you can also interpret this derivative a little bit more concretely in the sense that if y is our prediction and t is a target, it's saying if y and t are really far apart, then a small change in y can have a large impact on the overall loss value. So that's like a more concrete interpretation of the gradient of the derivative in this case. We continue throughout the graph. So you'll recall that the partial y, partial z is going to equal sigmoid prime of z, which equals sigmoid of z times 1 minus sigmoid of z. And then finally, we can compute the very last step, partial z, partial b. In this case, z equals wx plus b. So what that means is if you move b by a little bit, z is going to move by the same amount. So this is just 1. We can similarly compute partial z, partial w, which equals x in this case. So the derivative of z with respect to w is the x, or sort of the magnitude of our input. All right, so this actually isn't too bad if you write it out in these simple symbolic forms. And now we're just going to express our notation a little bit more compactly so we can tackle more general cases where the computational graph can look potentially trickier. So the notation we'll be using throughout this lecture is this bar notation, where you'll note that in general, we care about only computing the derivative of each variable with respect to the loss. So we want to know how a small change in that variable changes the loss, because that's the interpretation of how gradients work. Like our goal is to minimize the loss function. So because we only care about the derivatives with respect to the loss, we can compress the notation a bit by defining y to be equal to partial L partial y. And in general, for any variable in our computational graph, we're going to denote a to be partial L partial a. So in math, this might be more precisely expressed as the total derivative. It's okay if you don't understand the term. The overall conceptual thing you should have in mind is that we're trying to track the effect of a variable a throughout the entire computational graph. So a might affect the loss in multiple different ways. And our bar notation is capturing the total sum of all of these individual effects. So that's why it's called a total derivative. The second advantage of this bar notation is these are values our actual program is computing. So implemented in code, it's the precise value of this derivative at the input data and given parameters of the network. So when you're implementing this in a Python program, for instance, each of these variables corresponds to numerical values, and by expressing it in this bar notation, it sort of more strongly corresponds to the interpretation you have in code. Okay, so that's the motivation for the bar notation. We're now just going to work through two examples where the computational graph becomes slightly trickier. So the first example is the L2 regularized regression, where we have the same computational graph as before, but now we also want to regularize the magnitude of the weights. So we're defining this additional term r equals 1/2 w squared, and then we add a penalty to the weights with magnitude lambda. So one thing you'll realize here is we say the fan out of the variable w is now greater than 1, meaning there's two paths from w to our final loss, L reg. And that's something our old univariate chain rule can't quite deal with anymore. And this is actually the more general case. Like you can consider for neural networks, if we draw out the computational graph for a neural network, it might look something like this if we have one hidden layer. And you can see here that if you look at the intermediate variable z1, it's going to affect both y1 and y2, which both affect L. So now we again have two paths to the final loss. One other thing to note here is that previously we've been primarily writing our computational graphs like this: x goes to y. So our neural network has like a linear layer, remember, going from x to y. But this linear layer is composed of a bunch of different connections, right? So if x had 2 units and y had 3 units, or could be H1 more generally, we would have connections from every unit in the first layer to every unit in the second layer. And we label the connections like W sub 1, W sub 2, 1, and so on. In this computational graph form, each of these intermediate weights is something that we want to keep track of, which is why we're sort of transposing the notation a little bit and putting these nodes in red over here, because our goal is to compute the gradients with respect to the W's and the B's. So every variable that ends up in the final expression here, we're going to take the gradient. All right, so to deal with this fan out greater than 1 problem, we need to apply the multivariate chain rule, which says that if f is affected, has dependencies on t through two intermediate variables, x and y, to compute the multivariate derivative with respect to t, we have to add up two terms. So we have to add up the influence through the variable x and also the influence through the variable y. So in general, if there's more intermediate variables, we also have to account for each of those. And you can prove this formally. The rough intuition, which you also more or less use in the formal proof, is that if you make a small change in t, that's going to make a small change in the values of x and y. And because f depends on both x and y, small changes in x are going to have a small change in f, and then small changes y have a small change in f as well. And as you take limits, it ends up being exactly dependent to the product of the derivatives summed over each of the intermediate variables. If you want some practice with this chain rule, you can go ahead and walk through this example down here where you can compute the partial derivatives, add them up, and that gives you your total derivative. Okay, so in the context of backpropagation, this ends up actually being implemented really neatly in the sense that if we want to compute the derivative of f with respect to some variable t, if we choose the order we compute the derivatives, then we actually only need to compute half of each of these expressions. So in particular, if x and y are the children nodes of t in this graph, we want to make sure we compute x and y first, like the derivatives of f with respect to x and y. In this case, we want to compute x bar and y bar. And then we also know how the function t affects x and affects y, because that's how we define our computational graph. Like we define this potentially rich expression of computations. So when we want to find the derivative with respect to t, we actually only need to compute two more variables. So we want to compute dx dt, so how a small change in t affects x, and also dy dt. So these two terms represent the work that needs to be done. While x bar and y bar are variables we save in our code, and we can just use them, multiply them with dx dt and dy dt, and then add them up. So more compactly in our notation, we can write this in this current form where the variables on the left side, the bars, are already evaluated, and we have to compute dx dt and dy dt at our current node. Okay, so the way the backpropagation algorithm works is you consider an ordering of all the computational graph. This is actually relatively straightforward in the case of neural networks because we have linear layers composed on each other. And during the forward pass, when we're trying to compute our predictions, we go through our computational graph and compute each of the intermediate function values, eventually arriving at our prediction. The backward pass is you're just going to reverse all the directions of the arrows and then go in the opposite order you arrived at the prediction. So we're going to compute each of the children nodes and go backwards through the graph, eventually getting each of our derivatives.